Okay, shall we get going again? We've got lots to fit in today. That's all right. No, we're starting again. We've been really helpful, just for me to understand, because you're all part of one of there's another module that you're working in groups on. Just be really helpful to know like which groups are being represented here, because then as and when we come to your own personal brief, I could try and sort of think, oh, okay, well, in week 4, week 6, week 8, maybe we could do this instead. So we just sort of start from wherever. Let me know who you are and what group you're part of and what your kind of brief is at the moment. Anyone want to go first? Otherwise, we'll just sort of start at the end and then move on. But yeah, go for it. Part of? Gothic timber. Yeah, got it. Yeah. I can't promise, but if you say your name, I'll try and remember it. Kine. Sorry, I can't hear for some reason. It's all these wonderfully designed acoustic baffles. Kai, brilliant. Gothic timber, Kai, excellent. Are you enjoying yourself? Yeah. Good. Gothic timber is pretty cool, right? Yeah. Bending stuff, making stuff out of woods. Yeah, cool. Yeah. I'm gonna have to try and get this right. Sampiotta. I'm really sorry. This is very embarrassing, isn't it? I will do my best. Yeah. Okay, cool. Yes. Yeah, cool. I think, I remember seeing most of your presentations, so I'm kind of trying to put everything together in my mind. Yeah. Oh, really? Oh, okay, you switched. I didn't realize you were allowed to do that. It was their special dispensation. Okay. All right. Yeah, cool. Oh, the cob, the monster. Cob monster. Yeah, cool.
My name is Fatma. I was in the urban mining group, but now I'm in the cob.
Oh, there's a lot of. Is this like musical chairs? There's a lot of moving around. Thanks, Fatima. Yeah.
I'm Sim. I'm also in the cob group.
Oh, okay. Oh, this is the little cob corner.
Yeah. Cob community.
Yeah. Should we go over to you?
I'm Pink and I'm in digital timber.
Digital. The Gothic timber.
Yeah.
With Kai.
Yeah, with Kai.
Kai and Ping.
Yeah.
Excellent.
I'm Chan from Urban Mining Group.
Urban mining, same with the stone.
No, not stone.
Oh, are you doing? Was this the group with the
with the
ceiling tiles, the roof tiles?
Yeah.
Okay, got you.
My name is Agman. I'm in the stone group.
Cool. Agman.
Ayman.
Okay, yeah, cool.
I'm second year in GS2. I'm now in DCM.
Oh, that's cool. That's good. We're all here to learn. You and me both. Well, everyone knows you.
Yeah, I'm Ali. I'm also an ex-DCA student.
Cool.
I'm second year now, and here to assist you.
Yeah. Oh, so far, none of this would happen without you. So, well done.
I'm Andrea.
Andrea?
And I'm the
With the stone.
Yeah, with that.
Sam. Great.
I'm Shida. I'm in urban mining.
Cool.
I'm Hunter. I'm also from the urban mining group.
And the urban mining group is the stone one, and the retrofit one is the roof tiles. Is that right? Or is that kind of they're the same?
Well, it's the same for this semester, but for the previous semester it was kind of different. The stone group was working on.
Okay. Oh, well, this is fun. And what I'm glad about is that there's lots of different groups represented. So hopefully there's something that you'll learn here that you'll take back to any group that you're in. Okay, great. I can't promise to remember your names, but I'll try my best. what I want to do is very quickly look at, by the way, save your work. The thing that everyone talks about with Fibonacci is then people say things like, oh, Fibonacci is in nature. And you kind of go, yeah, okay, great. But I don't walk out into the world and see these numbers like 1, 1, 2, 3, 5, 8, 13. Like, I don't just see these numbers floating around. So what do people mean when they say that Fibonacci is in nature? And usually what you'll see is these kinds of images where you've got this spiral. And you might well be thinking, well, okay, I see that there's a spiral and I see that there's this series of numbers, but how do they have any relation to one another? So this is yet another one of these really good examples where a computer just talks in numbers, but we want to talk about geometry and shape and curves and 3D, right? And those numbers aren't very useful to us until we've done something with them. So what we're going to do, coming back to our brief, is we are going to take the output of one loop, which is our list of Fibonacci numbers. I'm going to do something with that. And actually what we're going to do is we're going to take those numbers and we're going to feed them into another loop. And we're going to use that to create what everyone talks about when they visualize Fibonacci spirals or squares or numbers. So the way this works is super simple when I explain it. But would it have been simple if I wasn't explaining it? Good question. But the way we're going to do this is exactly the same as we did here, right? We started with a linear approach. We didn't get into the loop until we understood what we were trying to do. And then when we understood what we were trying to do, then we built the function that would do it. So what we're going to do is we're going to start at a point. I might draw this on the board again. We're going to start at a point. I'm going to draw a square of side 1. So we're going to go 1, 1, 1, 1. So there's a square. And it starts at this point. Then what we're going to do is we're going to go to the opposite corner of the square, which in this case is here. I'm going to draw another square. But if I just draw the square in the same way as I drew it before, it's going to go like this, right? Not particularly helpful. What I want, make a mess on the board, is to rotate the plane in which that I'm going to draw that square by 90 degrees. So instead of drawing a square off and up and to the right, I'm going to rotate the plane in which it's almost like I take my piece of paper and I rotate it 90 degrees and I draw the same square. So instead of drawing a square that goes up and to the right, I'm going to draw a square rotated 90 degrees that goes up and to the left. I've taken this square, I've moved it, I've rotated it.
But then how would it continue? What would it look like?
Right.
Would it be on top of each other?
And then I go to the opposite corner. I rotate my red plane of reference 90 degrees. So instead of going like this, I rotate it round and I'm going to draw a square of side, well, in this case, 1, 1, what's the next number? 2. I'm going to draw a square of side 2 that goes there. And then I'm going to go to the opposite corner of my square, rotate my plane of reference 90 degrees, and draw a square of side 3. I'm going to go to the opposite corner, rotate my plane of reference 90 degrees, and draw a square of side 5. 1, 2, 3, 4, 5. Go to the opposite corner, rotate my plane of reference 90 degrees, draw a square of side 5, 6, 7, 8. Do you see how this is working? And every square fits in around the squares I drew before. And then when people talk about the Fibonacci spiral, what they mean is that. You're going from the corners, in fact, actually, no, that starts there. You're going from the corners that you use to draw the square each time, and you draw it with an arc. Yeah? So it looks cool, but now what we have to do is everything that I've just talked about is kind of makes sense in your mind when you're holding a pen and using a piece of paper. Try drawing a little sketch of it. Use squared paper if you've got any. Do a little doodle. And just try if you can sort of figure out exactly what the processes are. Makes sense when you're holding a piece of paper and a pen. But a computer doesn't have a pen and a piece of paper. A computer just has numbers. So now we have to figure out, well, what are we telling the computer to do? And the first step of that is that we're going to make it happen in Grasshopper in a linear way. So we're just going to do 1 or 2 iterations, and then we're going to make that loop happen. Okay? Do you want to just take 30 seconds, see if you can understand what the process is that I'm doing? Cool.
The only thing that confuses me is when you say like side 2, for example, what like...
Oh, a square of side 2 just means a square which has a length of 2 and 2.
Okay.
And a square of side 5 would have 5 along there and 5 along there. And every single one of them is a square, so it makes it much easier because it's not a rectangle where like one is different to the other. Are you sort of getting what we're trying to achieve here? There's a cool little this is your hand. And so if you measure the distances between your knuckles, what you'll notice is that this little guy here and this little guy here are kind of the same length. And that guy there is kind of roughly twice those two lengths. Suppose those two lengths added together. And then this distance here is that plus that. Roughly. I mean, nature is a little bit wibbly sometimes. Cool. We don't need to spend huge amounts of time, but do you kind of get what we're trying to do here? Yeah, you can kind of visualize it now. Pen and paper, always the first thing I reach for. So what we're going to do is we are going to go into my sort of split screen approach here. And we'll start at this point over here. In fact, I'll go into my top view. I'm going to start at this point. And the cool thing about Grasshopper is that you can turn a point into a plane. Have you tried to do this? Have you ever done this before? You literally you wire a point into a plane, and then that plane will then be the XY plane, like the ground plane, but centered around that point.
Can we also choose to put the XY plane instead of just plane? Or does that matter? If
you put the XY plane, it'll be centered at 0. But what I'm doing is I want to start at a particular point on my Rhino. But I mean, it doesn't make any difference. You can do it any way you like, as long as we start with a plane. And the reason we're going to start with a plane is because let's look at this plane here. It's got a green arrow and a red arrow. It's got an X direction and a Y direction. And when we create a rectangle in a plane, pardon me, let's just look at this guy. We create a rectangle in that plane. It's going to be going in that direction and this direction, the X and the Y direction of the plane. Now, if I take this plane, let's just play with this for a second, and I'm going to type rotate rotate this guy. Actually, I can do rotate plane. Yeah, here we go. Rotate plane. I'm going to feed this plane in here, and it's going to ask for an angle, and the angle is in radians, so I need to wire in a pi, and I need to wire in a number for the factor of pi. And this plane here, as I change the rotation, I can rotate this plane around. You see? See what we're doing? Nice and simple. But if I feed that plane into a rectangle and rotate the plane, I'm doing it this way. I'm just rotating the rectangle around that point. Cool. I don't need to do that. I'm starting with a plane that's just as it is. And then, well, the next step in the sequence of rules that I've just defined here is once I've drawn that rectangle in a plane, I'm going to go to the opposite corner. Well, the opposite corner, this plane has an x-axis and a y-axis and a z-axis. And I know how big my rectangle is because I've told it to be of size 1. Because that's the first Fibonacci, or the first Fibonacci number that isn't 0. A rectangle of size 0 is kind of just a point. It's like nothing. So we're going to start from 1. We're actually starting with the Lucas numbers, not the Fibonacci numbers, but don't worry about that. But then if I take this point here and I move 1 unit along the x direction of the plane and 1 unit up the x direction of the y direction of the plane, then I've reached the opposite corner of my rectangle, right? So I've taken this plane and I've deconstructed it. And a deconstruction of the plane gives me the origin, the x-axis vector, and the y-axis vector. I'm going to feed those vectors into 2 things here. The first is a multiplication, because that vector is just a direction, and it's a unit vector. It's 1 unit in that direction. If I rotate the plane, it's still going to be that length. That vector isn't going to be the length that I want it to be. So what I have to do is I multiply the vector by the size of the square that I want. So if imagine this is a 5-sided square, a 5-size square. It goes 5 units across and 5 units up. I need to take my x-axis, which is currently 1, 0, 0 in the x direction. I need to multiply it by 5 to get to this corner. And then I need to go up, and I need to multiply that by 5 to get to the top corner. So I'm going to multiply it by this guy here, the size of the square that I'm drawing. And then I'm going to do the same thing to the y-axis. I'm going to add those 2 vectors together. So we're effectively going 1 along here, 1 along there. The resulting vector is the addition of those 2 vectors, which takes me from this corner to this corner. And now if I turn that on, it's moved the plane from here to here. So we're moving a plane in a particular 2 sets of vector directions. Then I'm going to rotate that plane. Remember, by the way, green is up, red is across. Now I'm going to rotate that plane 90 degrees, and now green is that way and red is up. So I've rotated the plane 90 degrees. Once I've rotated the plane 90 degrees, well, we draw the next square. And the next square happens to have a Fibonacci side of 1, still 1, because 1, 1, then 2, then 3. And we do exactly the same thing again. And I've drawn this little line in here that kind of separates it out. Are you following along with me? Are you creating this definition as you go? Cool. Then we draw the next square. And then we go the opposite corner, and then we rotate the plane. And we could keep doing that for a long time, but it's going to get really, really boring. So what I'm going to do is, now that we're happy with that approach, the linear approach, we're just doing 2 or 3 iterations. Now let's think about how we're going to loop this. So the first thing we're going to do is we're going to bring in the values from the previous loop output. And I'll make this on the right-hand side so you can follow along, and we'll do it together, okay? So the first thing I need is this guy here. These are all my Fibonacci numbers. They look wrong. They're wrong because I started 4, 5. There we go. Started 0, 1. And there we go. They should be the same. Yes, they are. Great. So I've got my Fibonacci numbers here that I've created using a loop. I'm going to take the output of that. I'm going to use that in our next loop. And the way we're going to do that is I'm going to come over here and I'm going to start with a panel. And I'm going to connect this panel to the output that we got from the previous loop. And then, because I don't like these lines being really like all over my definition, I'm going to right click and do wire display hidden. And it turns it into like a little Wi-Fi signal. And if I click on the element, it will bring the line back so I can see what it's connected to, but it doesn't like disrupt my definition. So now what I've got is my list of Fibonacci numbers. Here we are. And what's the next thing we're going to do? Well, we're going to start at a point, and we need a starting place for our loop. So here we are. I'm going to set one point, and I'm going to select it in Rhino, or you can start at the origin, completely up to you. If you want to start at the origin, you can. We start at a point, and then I'm going to send that to a plane. There it is. There's my plane. I'm going to turn the display of that plane off just because it's a bit annoying. And then we need a loop start. I'm going to send that plane data in, feeding in a plane. And we need to know, well, how many times are we going to repeat it? I don't know, let's do 12. And we need a little button to reset the loop. There we go. And then we need a loop end to connect up. And this isn't receiving any data yet. We haven't passed any data in. And then what we're going to do? Well, one of the things that we did before was we had a list of all of these numbers and we added to that list every single time. There is a nice way that Anemone gives you the ability to record the data as you go around the list. So it means you don't have to maintain that list yourself. It's going to do it for you. And what we're going to do is we're going to start using the counter information, exactly like you asked. Well, here's the thing, right? You've got a list of all the Fibonacci numbers here, and they've got indices, and there are 26 there. So the first time round this loop, I want to read the first number, which in this case is actually 0. But let's ignore the 0, and we'll put an expression on that counter, and we'll say x plus 1. And now that's going to read the first index, not the 0th index. So that's going to start us off with a number 1. That counter is going to allow us to make a list item node that takes the index and then this list. And now look, the item should be saying 1 because that's the item that's at index 1. Now, with that number on this iteration of the loop is telling me how big my rectangle should be. And I have a plane to draw it in. So all I need to do is type rectangle, and the x size and the y size is going to be given to us. And the data is the plane. So as I click on that, this has gone green. It's drawn me a rectangle that's offside 1 in the right plane. Now, actually, what I'm going to do is I'm not going to draw the rectangle just yet. What I'm going to do is I'm going to use the loop to do all of the plane rotation and movement functions. And then I'm going to let Anemone do something really helpful, which is the end of the loop. If you right click on it, you see where you zoom in, it says constant output. That means that it's outputting the last thing in the loop. It's going to loop 12 times and then give you the last thing. But if you right click on it and do record data, now it says constant and record. Well, constant and record, what that's going to do is if it loops 12 times, every single one of these outputs is going to be stored in a list. And then it's going to give me all of the list of all the things that it's produced. So what I'm going to do is I'm going to feed in a plane, and I'm going to do a series of loops which move the plane, rotate it, feed it back in. Move it, rotate it, feed it back in. Move it, rotate it, feed it back in. And then I'm going to end up with a list of planes that are in the right places and in the right rotations. And then I can use that list of planes to create a list of rectangles that go in exactly the right place, of the right size. Yeah, cool. So here we go. I take my list item, which is in this case 1, and I'm going to move the plane. I think the way I did it, yeah, I did it exactly the same way as I did before. We're going to deconstruct it, deconstruct plane. We're going to move it 1 in the x-axis direction and 1 in the y-axis direction. So I need a couple of multiplications here. 1, 2, x-axis, y-axis, times 1, times 1. Then I need to add those vectors together to make one single movement vector. And then I'm going to take my plane that's come in and I've moved it here. So I've used a motion and a move tool here. Are you following along so far? Making some sense? However, I'm not quite done yet. I've got a plane. I've moved it to the opposite corner. In fact, if I now see that, look, the green and the red lines have moved to the opposite corner of the square. So I'm on to a winner. But then the next thing I need to do is I need to rotate that plane 90 degrees to the left. So now what I need to do is rotate plane. And if I was a little bit lazy, look, I've already got a definition for rotating a starting plane. And all it is a number slider 0.5 times pi feeding into a rotate plane with a plane input and an angle input. So what I can do is just copy this from my linear definition. Here we go. I'll get rid of that. And instead of being attached to this, I'm going to attach it here. So then this rotates the plane. And then, now I'm done, I feed that back into the data. And then I want to have a look at what I've ended up with. What I've ended up with should be 12 planes. There you go. You can see there's one here, there's one here, there's one here, 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 here. And they're already starting to look a little bit like if you just join them all up, they'd be like a spiral. Now those planes are all very well and good, but now I want to draw the rectangles in place. So I'm going to put a little scribble to remind me what I'm doing here, which is draw the rectangles. And now what I want to do is I want to make one of these, and I need an integer value for each one of the rectangles, and I'm going to feed in the planes. However, you'll notice that these planes are part of a tree. The line is dashed. So the data structure of this is being added to by the loop component. All I need is just a simple list. So all I need to do is flatten that down. And now I've got my list of planes, just a flat list. I'm going to feed that in here. And what I need, ideally, is the first 12 integers to match up with the first 12 planes that I've created using the loop. And that will draw those rectangles in the right place. So all I need to do is bring this number over here, or this list over here, all the way across, and feed that into my integer value here.
Why do you flatten the data?
Why do you flatten later? Oh, this one here. Oh, flatten the data. Oh, okay. So imagine you're the loop component and you're thinking, right, okay, so I've gone around once and I've got some bit of data that's been, the user has done something with. I've asked it to do something with this data. Then I've gone around again and I've got some other bit of data. Then I've gone around again and I've got some other bit of data. It doesn't know what you want to do with that data. So what it does is it puts them all in different branches of a tree, and then it allows you to filter through that tree and do what you want with. So effectively what you're doing is you're saying, this is the data from iteration 1. This is the data from iteration 2. This is the data from iteration 3. And they're all branches of a tree. But if all you want is just the result of iteration 1, 2, 3, 4, 5 in a list, all you do is you take that tree and you flatten it into a list. And that's all I want at this point. Now, this is probably, oh yeah, there we go. Because I fed it through a panel, it turned it into text, which wasn't very helpful. So I've connected that up now. And here are my rectangles. And almost certainly something's gone wrong. Ah, yes. It's a whole load of mess. So now we have to figure out, well, why is it going wrong? Well, a couple of things, right? The first rectangle that I assumed would be the case would be one that started with 1. But I'm feeding in a list of integers that starts at 0. So it's all offset. So it's drawing these squares, but they're the wrong sizes. And they're on the wrong planes. So all I need to do is I need to take this list and I'm going to shift that list. Oop. Here we go. I'm going to shift it, not 1 along. Oh yeah, there we go. That should work. I'm just going to give myself a little number slider to figure out exactly where we need to shift it. There we go. If we shift it 2 along, the reason for that is that the first iteration doesn't actually get counted in the list. So all I've done here is I've shifted it until it just suddenly flips into place. And I'm going to turn off this. And here we go. So here's our starting point. 2 squares of side 1, side 2, side 3, side 5, 8. Boop, 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 and we can keep going. And now these squares here, do you remember my list had 26 of them? But I only generated 12 planes. So it doesn't know what to do with the rest of the 14. So all I need to do is as I drag this up to the same kind of number, it's going to keep adding the planes in place and the rectangles will find a home because the 2 data lists are going to match up. There we go. And you can kind of see it drawing in this cool way. So now there's 25 of these spirals and you can zoom all the way in and all the way out. And you see how self-similar it is. Like as you zoom out, it kind of looks the same as it did when it was zoomed in. All just from a simple sequence of add the last 2 numbers together. And now you can get this geometry that's very complex. How long would that take you to do by hand? Well, for 25, probably about the same amount of time. But for 100, very different.
So, in the integration, you multiplied 0.5 by, where you multiplied with that?
Say that again. We've multiplied the... This one? Yes. This is a rotation of 90 degrees. But Grasshopper doesn't like 90 degrees. Grasshopper wants radians. Did you remember in my GCSE maths, this is a circle? Yeah? A full circle is 2 pi radians. So half a circle is pi radians, and a quarter of a circle, which is what we want, 90 degrees, quarter of a circle, is pi divided by 2, 0.5 times pi.
But if we were to put the angles in degrees and we offer 90 degrees, would that work?
Yeah, well, if you hover over this guy here, it will say rotation counterclockwise around plane z-axis in radians. So what you can do is you can type radians, and this will give you an ability to put in degrees and put out radians. So if you found it easier, you could do this, and it would give you exactly the same result. It's just that I think of this as how many pies. Yeah, makes sense? Yeah?
Would you be able to repeat just the last part regarding the rectangle?
Yeah.
Where did you get the list from?
Yeah. So actually, this is a really, really good question, right? Because this is kind of what we're trying to do with the whole approach. We've done a loop and we've generated a whole load of numbers. Then we've taken that list of numbers and we've fed it into the next loop. And then the output from that loop, then we've done something with that. So the results are add the numbers together to get to generate the list of Fibonacci sequence. Then generate the list of planes from that list of numbers. Then once you've got the planes, add the rectangles to it. So you're asking exactly the right question. How do I know where the numbers have all come from? Right. This is a panel, which is the output of my Fibonacci sequence. All I've done is just connected those panels together. And what that means is, if I change my starting numbers here, I can see a different Fibonacci spiral. Let's try it. I mean, I don't know whether it's going to work. Yep, there you go. It's completely broken. But, you know, it's a nice starting point, right? You can get some nice, interesting, you can now start play with the whole process, because now I could reimagine what my Fibonacci sequence looks like, and that's going to affect all of my rectangles that get drawn. Yeah?
I just asked that because the output, the rectangular output, I think I did it wrong. Maybe I missed a step.
Are your rectangles like all over the place?
There's no rectangle.
Oh, there's no rectangles. So the thing, do you see what's going on here is as I shift that list, basically the rectangles are too small for the planes that are going in. So I need to shift it twice up to get rid of that first 0 and 1. And then all it's doing, I'll get rid of this panel because it's a bit confusing. This is probably easier to see. This list of Fibonacci numbers, I'm just using those to drive the size of the rectangles. That's all I'm doing. So this is my list of Fibonacci numbers. I send that list, I shift it twice to get rid of the 0, which we don't want, and the first one, which the loop does, it just ignores. And then I send that list of integers to drive the sizes of the rectangles, but I also feed it a list of planes.
The plane is the end of the loop, right?
The plane is the end of the loop. Yeah. And because I happen to have 26 perfect planes that are positioned and rotated correctly, and 26 perfect sizes of rectangles, the rectangle just goes, oh, I've got 26 planes, I've got 26 numbers, I know what to do with this.
Yeah.
Also, I have a very small question.
Yeah?
In the beginning, we got the values from the previous loop.
Yeah.
But also we add a number slider, and it's now 25, right?
So
Very beginning.
So
Yes.
Yeah, so what
Here I have something different, I guess.
Yeah, so what you can now do is tie this together, which is just with a list length node. And instead of a number slider, I just want to use however many of these I have. Yeah. And then I can just get rid of the slider completely. I don't have to manually type that in. I just say, well, whatever I've generated, that's how many times I need to go through this loop. And then you'll see it's working kind of rather nicely.
Sorry,
Yeah.
I'm sorry for all the questions. But
No, questions are good. This is good.
Checking my script.
Yeah, okay. Have it. Do you have a question while we're... The same problem. Okay, let's go and have a look, see if we can see the same problem.
So I got the planes. They're rotated, but I don't know why the rectangles are not.
So if you hover over that, you'll get an error that says data conversion failed from text to plane. And it's because you've typed, that was exactly the same mistake that I made. I connected up to the panel, but the panel just reads the text. And now I get rid of that panel because it's kind of confusing. Yeah, there you go.
Okay,
Done.
thank you.
Ah, you're having a great time. Wow, you've done a really cool thing there, man.
You didn't get this.
It looks like you're rotating slightly wrongly, but also potentially. I tell you what. So you've changed gradients to gradients, but then you've multiplied the gradients by pi, which you don't need to do. So just take that guy out and feed that straight in, and then reset. Okay.
You just need to.
It's very pleasing, and the whole thing comes together. It's very like.
What happens?
Right.
Yes.
Yeah.
It's just like okay, so one thing.
No, it's just playing this plays off. You can kind of see what's there. How many times are we running this? Yeah, 23. It looks like motion. Good spot. Okay. Around. Great. Another pair of eyes always helps. Right, I'm really keen that we start to move on and not just sort of play around with these kind of little things. Let's just make sure we save our work. Duh. Now, I've been weighing up whether there's another thing that I want to show you that is very similar to Fibonacci. I think with this one, I'm going to show it to you, and then you've got the grasshopper definition, So go away and try and recreate what I've just shown you. But I don't think it adds a huge amount, but there is a really cool little thing that I want to sort of bring to life a little bit. So actually, I'm going to demo this rather than you work through it at the same time. And it is something called L systems. Ever heard of L systems before? Anyone come across L systems? No? L systems are really cool. And they have some oddly interesting relationships with the Fibonacci sequence, which we just looked at, which is that the way they work is they model growth. They model biological growth. So if you have a Google for an L systems, an image, what we're going to do is we're going to be able to produce this kind of thing. And you start at a starting point, and then there's this kind of branching that happens. But every time that branching happens, you end up with two more ends of a branch, and then that can branch as well. And then you've got two more ends of a branch, and then that can branch as well. And that's how trees form branches, right? You start with one trunk, and then it splits into multiple branches, and then multiple branches off that. And then at the very end, you've got like little tiny twigs and leaves and all sorts. And the way L systems work is that it's trying to do a mathematical model of how that branching happens. Because when you look at a tree, you don't think, oh, there's maths. You just think, well, there's a tree. But the way it works is quite interesting, actually. It's that what we're going to do is we're going to turn our attention from numbers to letters. And L systems is what's called a grammar. And a grammar is a technical term, but basically what it means is, I'm going to turn this guy off so you can't see it. There we go. We're going to start with a letter A. And that starting point, in fact, I can draw this on the board, right? Maybe this is a good thing to do. I'm going to start with a letter A. It's a string, just a series of letters. That's all it is. And I'm going to give you two rules. The first rule is, whenever you have an A, you can turn it into an AB. And whenever you have a B, you can turn it into an A.
So this is like an outside rule.
These rules are they're rules, and this is the start. Do you remember that slide I put on? You have a starting input, you have a set of rules, and then you end up with a sequence. It generates a sequence. This is my starting point, and these are my two rules. And I will apply those rules whenever I can to my string. And every time I apply those rules, that's one iteration. Now, you might think to yourself, this doesn't feel very much like trees. This feels a bit like, I don't know, English or maths or something. Well, so what we're going to do is, every time there's an A, we can turn it into an AB, and every time there's a B, we can turn it into an A. But we can only apply these rules once per iteration. So my starting point is A. Can I apply the first rule? Yes. So this is iteration 1. This is iteration 2. I can apply the first rule, and that says whenever I find an A, I can turn it into an AB. So my A turns into an AB. Aside from here, can I apply the second rule? No. So that second rule completely useless to me right now. So I've moved from 1 to 2, and I've gone from A to AB. Fine. Very exciting, you might say. Okay, well, let's try the third iteration. I'm going to apply it to this. First rule, can I turn an A into an AB? Yeah. So what do I end up with?
AB.
Can I apply the second rule?
Yes.
Yeah.
ABA.
Cool. Fourth, I'm done with the rules now. So fourth iteration.
ABA.
So A turns into AB, B turns into A, A turns into AB. Yeah? And you can make a really fun poem. A turns into AB, B turns into A turns into AB, A turns into AB, B turns into A. Abba. Should we just keep going? A turns into AB, B turns into A turns into AB, A turns into AB, B turns into A turns into AB, B turns into A, and A turns into AB. Above. And again, you're like, okay, who cares? One really cool thing about this is that these rules don't seem to have anything to do with Fibonacci, but count the number of letters in each one of those strings.
1, 2, 1, 2, 3, 5.
What do you notice?
The same as GC.
It's the same as the Fibonacci sequence. Well, kind of apart from the 2 ones at the beginning. 1, 2, 3, 5, 8, 13. And you think like, well, this is weird because my rule doesn't say add the last 2 numbers together. My rule says if I have one letter, I can turn it into 2, and if I have another letter, I can't turn it into 2. But the result is the same, which is super cool. Here's the other cool thing about L systems and the way this works. I'm going to try and, if I can, get rid of this data structure thing. There we go. With them, these letters, just the same as the Fibonacci sequence, can turn into rectangles. The letters can turn into branches. And the branch goes like this. I'll go down rather than up. Maybe I'll go up. It looks more like a tree if I go up. So I'm going to start with A. And the rule is A branches into AB. So an A turns into 2 branches like this. But a B only goes to A. So A branches to AB, and that's my first iteration. Then I go A branches to AB, but B only goes forward to A. Do you see how this is going to become a tree? I've gone from letters to a tree. But letters you can do with a computer, trees you can't. So what you do is you do the thing that you can do with the computer well first, which is just pushing and pulling these letters around, or these numbers or whatever, and then you turn it into some geometry. So A branches to AB, B goes straight ahead to an A, and A branches to AB. Can you carry on drawing? Yeah? Does it look like a tree? Yeah, sort of. This is a really simple L systems. There are much more complicated L systems. And in the notes, there is a link to this guy here, which, yeah, here we go. This is what you can create with more complicated L systems grammar. It's very cool. This whole paper, if you're interested in maths, yeah, here you go. This is the example of what exactly we're looking at here. A turns into AB, AB, A, B, A, 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 B, A, B. And if you're not sure about how to turn an algorithm into something that a computer can understand, usually someone's done it for you before, and they've written a paper about it, and you can read the paper and understand it. So I didn't come up with this. Like, I'm not that much of a genius. Someone else has written the paper, and they've spent their like PhD or their life's work like working out how these letters are going to turn into this thing. All I do is go, okay, great, thanks for doing that work. I'll credit you in my acknowledgements. I'll add your paper to my bibliography, but I'm going to use it to generate something. So let's look at let's look at this. I've got starting point A. I've got a loop start. I'm running it 8 times. Loop end. And the text rules are A turns into AB and B turns into A. So what I do is I take my text that comes in, I split it into a number of characters, and I say if the character matches A, then replace it with an AB, and if the character matches B, then replace it with an A. And then I send that result back out and I loop round again. It's kind of very similar to the Fibonacci sequence, and you'll see there, then I can generate these with incredible complexity. In fact, if I keep going, that's 19 of those, and that's what I end up with. That's only 19 iterations, and it's that long already. So you remember when I said that computers can generate huge amounts of complexity that takes them billions of years to solve very, very easily? This is kind of a good example. All I did was just nudge a slider, and now I've got a string that's like hundreds and hundreds of characters long. And there's my terrible drawing of exactly what's going on here. And then I can add some geometry to that. I've got myself an A curve, which is here. I've got myself a B curve, which is here. And every time I have an A in my list, I'm basically sending this in. Every time I have an A, I branch out. Every time I have a B, I go straight. And I end up with this guy here, which is starting to look a little bit like, I don't know, some kind of tree or something. Now, this is a little bit more complex and probably something for you to have a play with in your spare time that you have lots of this week. But the thing to not lose your mind over is this guy here. I've highlighted this in purple. This is the text generation stuff. And all I've done is copied it over, and it's exactly the same. So this looks complicated, but all I've done is just taken what I've done before that I know works and copied it in. That's pretty much what I want to show you from L systems point of view. But especially if you're thinking about projects involving growth, L systems are something to look into. And there's also a plugin called Rabbit, which allows you to play with L systems in a bit more of an interesting way. And you can effectively, you're typing different grammars into this system and it will generate the geometry for you. We don't really have time to go into this but in great detail, but all that's happening is everything I've just described, this is putting that into computer language about branching a branch, and then I got 2 ends, and then I can move that branch and scale it to the ends of the existing lines. And then what I end up with is a whole series of lines. Yeah, I think we're doing okay for time. What I want to do is let's have 5 minutes for questions, and then I'm going to introduce you to something called surface flow. And then this afternoon, we'll have a loop with a fitness function and an evolutionary algorithm to solve it. And it's going to get very cool. Are there any questions whilst we go? Because I'm aware we're getting very mathsy, getting very technical. Is this kind of stuff that you have done before, enjoy doing, or are we like Kill me now.
It's something new, but it's just it's interesting.
Mm-hmm. Yeah. Which one are you looking at? Well, the Fibonacci one. Yeah. Okay. Let's have a look. So the plane coming in. Find this item. This one here, rotate plane. It does look like it's just like a unit. Right. You're on constant output. You right click that and click record data. And then reset. So now it's moving up to your output. And now it's looking into real thing.
Like Postman.
So there you go. Now it's not in. I think for some reason with this is missing one of the mission numbers. Okay, there you go. Well, it's working out. All we need to do.
That's what I tried to do.
It's kind of working. And then as you drag this up, now it's going to place all of it. With the cost output. Okay. Any other questions before we move on? Any other questions on this before we move on? We're going to look at something that I think is a little bit easier to visualize now, but will involve a little bit more maths. So you can have it one of two ways. Okay. Here we go. Oh, is this going to load? Yeah, here we go. Right. So we're going to look at this, which looks rather pretty, right? And what actually we're going to do is we're going to stay within this particular algorithm for the rest of the afternoon. And we're going to think about how we can push some of the control over this. Now, you may not be interested in this particular algorithm, but the approaches are going to be really helpful for everything that we're going to look at. And what this is asking the question, if I have a particular surface and a raindrop falls on that surface, which way will that raindrop travel? Yeah? Does that kind of make sense? So if you just picture in your mind an umbrella, and the rain is falling on the umbrella, and then the raindrop kind of like moves down the side of the umbrella and then kind of like off the edge. Woo, like a little lemming. Now, an umbrella is a like fairly simple shape. You kind of know it's going to go down. But what if we had a much more complex shape, like, for example, actually, I'm going to try and yeah, here we go. Like a double curved shape. As I spin this around in 3D, you can kind of see what's going on here, right? The raindrop falls on this shape, and then it falls down. But obviously then as it's falling, it kind of goes into this little valley bit, or it kind of joins up with all of its friends and kind of runs off in little rivulets. And exactly where does it end up? Well, that's quite difficult to work out mathematically. And it's quite difficult for you to picture, like, for any shape, where is this raindrop going to go? Well, you'd probably have to just like drop a raindrop on and watch it and just guess, right? But luckily, we have the ability to do some cool things here. So actually what I'm going to do is I'm going to turn this off. What we have going on is I've just placed three-point curves on the Rhino world. So if you're on Rhino 7, all you need to do is just grab a NURBS curve, 3 points, and then make 3 of them and drag the points up and down in some way. So you end up with 3 points that kind of maybe 2 of them go down and 1 of them goes up, 2 frowny faces, 1 smiley face, something like that. But as you play with it, you'll be able to see what's going on here. And then I'm going to loft between those curves. Very simple Rhino move, just loft between the curves. If I type show, actually you'll be able to see that there is one here. I'll go to shaded view. So here's my lofted surface. And yours will probably look different. I sort of hope that it does. You can sort of play with yours a little bit. And it's this double curved surface. And then all that's happening here is I've brought that surface into Grasshopper. And then we're going to do some really interesting things. This looks like a very simple loop. There's actually fewer elements in this loop than there were in the previous one. And that's kind of good because what it's actually doing is very complex, but we're able to optimize it for something that the computer can work out very, very quickly. And the first place I'm going to look is, do you remember me mentioning about diagrams? There's a website in here, and the easiest way of finding it is just to Google Wu J Sung surface flow. And you'll see a link to a PDF called Rhino Grasshopper Visual Basic Workshop. We're not going to work in Visual Basic, but the process is exactly the same. Hopefully this kind of image is like recognizable to you. It's kind of like the same kind of lines that we're producing. And if you scroll down and have a look at the second page, there's the thing that says idea. And it says the goal of the definition is to simulate the way water flows downwards on a hilly terrain. Let's start by dividing the process into 3 parts. Part 1, we're going to define a drain slope vector at an arbitrary point, called an input point in our definition, on a given surface, and then decide the possible position of an output point on that surface. When we're given a vector at a specific time and position, by multiplying a factor, we can predict what the next position would be. In our case, we call the factor distance factor, and this number will decide how precise the process is going to be. Everything I've just said there, I'm fully expecting you to be like, what? Because we're not mathematicians, but we're very visual people, us architects. And what we can do is look at diagrams. So let's take a look at this first diagram. This is our surface. This kind of hilly surface goes up, goes down, goes round, goes about. It's got all sorts of shapes. And what we do is we pick a point on that surface. maybe if I have this, no, I can't take this piece of paper off. I pick a point on that surface, and what we're going to do is we're going to try and figure out, if I was a raindrop at that point, which way would the surface make me want to go downhill? Well, luckily there's some maths behind this. And again, someone else has done the maths. I don't have to do it. I just have to understand the maths and be able to translate it. And the first thing is, what you do is you take this green thing, which is a Z vector. This is a vector pointing straight up at that point on the surface. Then I need a normal vector, which is the blue one. Everyone know what normal vector means? Perpendicular to, could be the XY plane, but it's usually on a surface, like a fluid surface. The normal vector is going to point in which way? 90 degrees. Yeah, you're kind of doing this. Yeah. Well, kind of up. But what if the surface was like this?
90 degrees to the point on the surface?
Yeah, okay, great. So we're a little bit more, we're trying to be really specific because we're going to need to tell this dumb computer what to do. The way I think about normals is I think about hair. So I've got a person's head, and I want to imagine they've got really spiky hair. Kai's probably got the closest. So what I'm imagining is that every hair is standing on end. Yeah? So here, that hair is pointing straight out, like this, right? And if there was a bit of hair here, it would kind of, do you see what I'm getting at? Yeah? And each one of these directions is what we would call the normal vector. So it's if you feel like a bit of your forehead and you think, okay, what would a bit of hair that points straight out from that bit of my head? Well, it would kind of go in that direction, right? That's what we're looking for. So that normal vector and the Z vector gives us all the information we need in order to figure out mathematically which way downhill is. And the way it works is you take this input point, you take the Z vector, which goes straight up into the sky, you take the normal vector, and you do the cross product of those two vectors. The cross product of a vector, you may remember from GCSE maths.
It's been how many years?
It's been a few years, right?
Yeah.
But the cross product of two vectors is at 90 degrees to both of them. And the way that you remember it is the right-hand rule.
Oh my God. Oh
You remember the right-hand rule? Is this coming back to you?
I remember it.
Yeah. So the right-hand rule says, okay, if I've got a vector which is my thumb and a vector which is my first finger, if I do a cross product of those two vectors, that resulting vector, cross product vector, is going to point perpendicular to both of them along my middle finger. And the cool thing is that the further apart those vectors are, the longer this one is. And if I bring these two vectors close together, if instead I actually have these two vectors that are very close together, the result is going to be really small. And if the two are 90 degrees to one another, it's as big as you can get. So the cross product is really useful because the cross product is then going to actually point in the direction of the contour of the surface. So it's going to point along the hill. But the cool thing is, if it's pointing exactly along the hill, all we need to do is just rotate it around 90 degrees. And if you're firing along the hill and you rotate 90 degrees, you're firing down the hill. That's all you need to know. It's like if you've got two choices, you can either walk around the contour line of the hill or you can walk straight down the hill. But those two are always at 90 degrees to one another. So all we need to do, take the cross product of these two vectors, rotate it 90 degrees, and then we're firing downhill. Then we do something cool, which we move that point along that vector. Now there's a problem, which is, here's my normal, here's my surface. I'm looking in like in section, I'm in 2D, right? and I move it, and here's the resulting vector. And I move down the hill. But we're on a curved surface. So I'm going to end up not on the surface anymore. I'm going to end up floating just a bit above the surface, or just a bit below the surface, because the curve doesn't let me go there in a straight line. So what I now need to do is the next stage is I need to take this point here, and I need to bring him down and put him on the surface again. And then I'm going to take a normal from that point. I'm going to do the same cross product, and I end up with this vector. And then he's not on the surface anymore, so I bring him down, and then I do the same thing again. And then I bring him down, I put him on the surface, and I do exactly the same thing again. Do you see maybe we're going to be using some loops? Yeah? This whole process, that's one little step, and then I'm going to feed that through a loop, and I'm going to do it maybe 100 times, and I end up with a curve. Yeah? That's why loops are so powerful. There is no way of generating these kinds of curves in one go. You have to use an iterative approach. Now, like I said, you may not care about these curves. I think they're particularly beautiful, but you may not care about it. But this is one of those things that actually, like many, many other things, you have to use a loop to solve the problem. We've got 5 minutes till 1 o'clock and we need to sort of pack up and go. So I think probably when we come back, we're going to look at 3 things in quick succession. The first is we're going to make, well, I've kind of done it on pen and paper already. So we'll tick the pen and paper box. Or you can draw a little thing in your notebook over lunch if you want to really understand what we're going to do. Then we're going to make a linear approach. So we're going to try Grasshopper without any loops. I'm going to just kind of, okay, what am I trying to do? How am I going to build this definition to do what I want to do? And then we're going to make a loop. And then we're going to feed the loop into an evolutionary algorithm that will allow us to control the output of that loop, which is going to be fun. We've got a couple of minutes for any questions, and then we'll break for lunch, I think.
Just I think about what you were doing right there. So how would that transition into the idea of the raindrop? Or will we talk about after the break?
Yeah, so everything that I've just done here, that's mathematically, that's giving you downhill, down a slope.
Okay.
And raindrops, we know, go downhill, down slopes. So what we're going to end up with is each of those steps is a little bit along the path that a raindrop will take when it goes down that surface. And when you then take all of those tiny little bits of lines and you draw them together, you get a curve on a curved surface, which is the path that raindrop's going to take. And this is just the way my mind works, because I'm trying to go from a physical process that I can see happening in real world. I'm going to try thinking, well, what is the numerical approach for making that work in a computer? And then I'm going to build an iterative way of solving that. Yeah. And this is, it's a fairly complex problem, right? Like, given any surface, you can't just sit down and draw that route. You don't know it. So it's a complex problem to solve, but you can work it out with this process. And we're very much standing on the shoulders of giants. Like, I haven't come up with this. This is a mathematician who knows what they're doing. And you go, okay, right, I need to find what's the vector process. And then I just need to translate that into Grasshopper. And you end up with, this is the route that the raindrop's going to take, basically. Oh, yeah, there you go. There's your right-hand rule. Yeah.
Actually, I took IGCSE. So
Oh, yeah?
I was able to do computer science, and this is the first time that I've ever heard someone say Visual Basic. Because I used it.
Yeah. Visual Basic is super cool.
And no one knows what Visual Basic was.
Yeah.
Oh my God, this feels weird.
By the way, just whilst this is on the screen, everything that I've just described, that by drawing on the board and all of this kind of stuff, when we say in the brief for this unit, diagrams to explain your process, this is what I mean. Yeah? This isn't just a screenshot of some grasshopper nodes. Someone has actually spent the time drawing this diagram correctly and well, and it's a kind of, perfect example of this is how I'm doing this. And you're having conversations about the numerical approach rather than like, I use this grasshopper node. You're saying, I care about flow on a surface, so this is how I'm solving that problem.
Would we be able to get the directions with the help of Grasshopper, but then, for example, taking it into Illustrator and giving
absolutely.
it color,
Yeah. So you could take this from Grasshopper and take it into Illustrator. Make sure that everything's the right color. You've got key. Look, here's this little diagram that I drew on the board, where you've got a curved surface, and then you know that you're going to get outside of the surface, so then you need to match it back to that point on the surface and all those kinds of things. To be honest, like the starting point for all of this is a sketch in your sketchbook where you plan out what the diagram is going to look like, and then you take it into Illustrator. And sometimes Illustrator, like I'm not sure I'd even generate something from Rhino in order to take it into Illustrator. I just start drawing this in Illustrator from a sketch, because it doesn't have to be accurate. It's just diagramming your approach. Are you also, I think over lunch, a really good question to start asking yourselves is, what is the problem I'm trying to solve in my design brief right now? Because this is a solution to surface flow along a double curved surface, which, I'm interested in, but you might not be interested in. But if you can articulate the problem that you're trying to solve, the complex issue that you're trying to get, then you might be able to find someone who's written a paper and published his PhD or something on that thing. And then you could translate it into a Grasshopper script that actually will do what you want it to do. So trying to figure out what the question is you're asking is a really good thing to try and do, maybe over lunch. Chat with the other people in your design groups. Say, okay, well, what's the complex problem I'm trying to solve? And then see if you can write it down. Okay, it's 1:00. We're in Gibbs after lunch, so I have to leave this beautiful new building. Do you all know which room we're in?
I think they have. Yes. We're in Gibbs, G110.
G110. Okay, great. I'll see you there then. Brilliant. Have a good lunch. See you in a bit.